Okay, for Learning Assessment 7.3, the problem statement is the switch in the network below opens at t equals 0. Find V0 of t for t greater than 0. And we're going to use our problem solving strategy entitled Using the Step-by-Step Approach. If we look, here's our circuit, and if we look at our problem solving strategy, we can see that step 1 is we assume a solution, and we know for this circuit that V0 of t is going to be of the form K1 plus K2 e to the minus t over tau. And now we need to use circuit analysis techniques to be able to identify K1, K2, and tau. Our problem solving strategy says next, draw the circuit at t equals 0 minus, and if you'll note, we've replaced the capacitor with an open circuit. We've assumed steady state. The circuit's in steady state before the switch is moved, and we replace the capacitor with an open circuit, and we're going to solve for the value of the capacitor voltage at 0 minus. And if we look at our circuit, we do a number of techniques to solve it. For instance, let's utilize some source transformation. So let's take this part of the circuit. We have a voltage source in series with a resistor. Let's perform a source transformation, and when we do that, we can redraw the circuit as follows. Okay, so now our voltage source in series with a resistor becomes a current source in parallel with the resistor. So we're just redrawing the circuit. Again, here's our variable of interest. Now, let's take these two resistors and combine them in parallel. And we know that two 2-ohm resistors in parallel will give us a 1-ohm resistor. And we can just, for instance, for the time being, we can just keep in mind our variable V0 out there. But if we go through and do that combination, and now we have a 1-ohm resistor for those two in parallel. Okay, so there's our circuit. Now, let's do another source transformation on that current source and resistor. And when we do that, here's our resulting circuit. Here's our capacitor voltage that we're looking to solve for. And we note now that, for instance, the voltage V0 has disappeared from the circuit because of the source transformations. Now, this is really a single loop circuit with a single current I1. And I1 can be calculated as 12 minus 4 over 4, or 2 amps. And now we can either go around the right loop or the left loop. So let's go around this loop to calculate VC 0 minus using Kirchhoff's voltage law. So VC of 0 minus then is, we've got two resistors in series, so that's 2 plus 1 times 2 plus 4, and that says the initial capacitor voltage is 10 volts. Now if we wanted to go back to our circuit here and just calculate the value of V0 minus. Okay, we could do that. For instance, we know this current's 2 amps, so that would mean that there's 6 amps flowing through that resistor, and that would tell us that V0 minus then would be 6 volts. So now we've calculated really what we're really interested in is that capacitor voltage. Now our next step in the problem solving strategy says, well, now let's draw the circuit at t equals 0 plus. We're going to replace the capacitor with a voltage source equal to the value at 0 minus. Again, remember continuity of voltage for the capacitor. So here is our capacitor. It's represented by that 10 volt source. Now we want to calculate the value of V0 plus, and if we look, we've got a simple voltage divider. So V0 of 0 plus, then we have 10 volts, and it's divided equally between those two resistors. So V0 of 0 plus then is 5 volts. Now our next step in our strategy is to draw the circuit at t equal infinity. Now we're going to assume the circuit's back in steady state. So we replace the capacitor with an open circuit. And there's our circuit. And again, we've really got a single loop circuit. We have a single current in this circuit, and we can get V0 of infinity again using voltage division. So we have 12. We want the voltage across this resistor, so we have 2 over 1 plus 2 plus 2, and that gives us 24 over 5 volts. Okay, step 5 of our problem solving strategy says now we need to solve for the time constant. We're going to use this circuit, and we're going to find the Thevenin resistance seen looking into the terminals of where the capacitor is connected. So our circuit is this. So let's look back quickly. Remember, when we're finding Thevenin resistance, we take that voltage source and set it to 0, and that becomes a line like this, and we're finding the Thevenin resistance seen by the capacitance. Okay. So in our case, our Thevenin, we've basically got these two resistors in series, and they're in parallel with that 1 ohm. So we have 1 times 4 over 1 plus 4, which is 4/5 of an ohm. And remember, for an RC circuit, the time constant is R Thevenin C. So we have 4/5. Our capacitance was 2, and that says we have 8/5 of a second is the time constant. Now our sixth and final step is here's a solution, and now we're gonna plug in values into our solution. So then V0 of t, the V0 of infinity we calculated was 24 over 5. V0 of 0 plus was 5, which is 25 over 5. And 8/5, remember, is 1.6. Okay, then so V0 of t is 24 over 5 plus 1 over 5 e to the minus 5/8 t volts.